Hey everybody, in this video we're going to look at the different types of kinematic variables or symbols that we'll see when we look at kinematics, both linear kinematics in one dimension or when we get to two dimensions. So let's take a look. First, we covered some already when we defined motion in class, and the very first thing we said was about position. We said if we need to see if something is moving or not, we look to see if it's changing its position relative to some background or frame of reference. So when we talk about position in linear kinematics, we're talking about a particular position in space, and because we're talking about linear kinematics, we're talking about a straight line, which could be in the x direction and have numbers indicating where on that line the object is, like I'm drawing now, negative and positive. Or we could talk about linear kinematics, motion in one dimension, that is vertically, which we would call the y, and we could still have numbers there indicating what direction the object is moving in, or whether it's in a positive or negative position, depending on where we choose to put our 0 point or origin. So we can call position x. That would be a position in the x dimension, horizontally. Or we could have a position that we describe as y. That's a position in the y dimension, somewhere vertically. We could also, if we have another dimension, because we're actually in a three-dimensional spatial universe, we could have a z dimension. That's how always I will write z. We don't get to the z dimension for a while, so that's not really a big thing for us to look at right now. The next variable that we want to look at is the variable that describes change in position or displacement. While position is simply a position in space somewhere, displacement is change in position. And we symbolize that with a delta x, delta y, or delta z. I'm just going to stick with x and y because we don't need to deal with any z's yet. So change in position in the x direction would be delta x. Remember, that's always going to mean difference or change in, and that means it's always going to be the final thing minus the initial thing. X final minus x initial. You can choose whatever subscripts you want. If there are only 2 points in time, you'd probably just use initial and final, but we could have 3 different points in time we care about, and so maybe it would be x3 minus x2, the third x position minus the second x position. Right now we'll just stick with xf for final position in the x direction and xi for the initial x position. We could have delta y, which remember would always be y final y position minus y initial. The displacement variable, or the displacement quantity, is one of the examples of what we call a vector quantity. A vector quantity has both magnitude, or an amount, that's symbolized by a number. So maybe that's, if it's displacement and changing position, the magnitude would be a number representing how many meters or miles that the thing changed position. And it also has a direction. So in our case with linear kinematics, it can either move in the positive or the negative direction when it changes position. So remember, magnitude is going to be a number, and direction is, for right now, just going to be symbolized by either a plus or a minus symbol. Later you can also use an angle to indicate direction, or something like north, south, east, west. After displacement, we talk about the next quantity, which is distance. The symbol we'll be using for distance is just a lowercase d, and we're not going to use it much at all, because usually we'll be dealing with displacement. A way we could define distance is total space traversed. Think what your odometer reads in the car. The odometer doesn't tell you what direction you've been traveling in. It only measures the total distance that you travel. Because it doesn't give you anything about the direction, distance is an example of a scalar quantity. Unlike the vector quantity, the scalar quantity only gives you a magnitude represented by a number. And we'll always have units for that. You know, if we have a certain distance traveled, it could be in meters, miles, or light years, whatever. Same thing with displacement. The magnitude is a number, but for that displacement, you still have some sort of unit because it's a physical quantity. So you're going to say a displacement that has a magnitude of 5 miles, 5 meters. But since it's displacement in a vector, you'd also give a direction in the positive or negative direction, at a certain angle, in the northerly direction, something like that. Our next thing we'll define is time. How can we define time? A little difficult. we have already an intuitive experience and understanding of time, but let's just say time is generally going to represent how long it takes something to happen, how long something takes. We symbolize it with lowercase t. Time is a scalar quantity for us, meaning we're not going to represent its direction. The forward march of time is always going to be going in one direction. We might as well call it the positive direction. If we were talking about a negative point in time, that would indicate something that happened before our stopwatch started, which we will actually end up seeing. But for now, let's just say it's scalar, and we have a magnitude represented by a number. No direction, just an amount. Next, we have the variable that will identify speed. How fast, right? Lowercase s is what we'll use to signify speed. Speed is actually a kind of combination of two different quantities. It's actually defined as distance over time. Because I have symbols for distance, lowercase d, and a symbol for time, lowercase t, I can just write s equals d divided by t instead of writing out the whole thing. Speed is a scalar quantity. It doesn't have a direction. So it's magnitude only, just a number and units. Miles per hour, meters per second, something like that. You can think of the speedometer in your car, right? It tells you how fast, but it doesn't tell you what direction you're going in. So it's not a vector. It just tells you how much, how fast, just the number and the units. Next up is velocity. As far as velocity goes, velocity could tell you the velocity at an instant, a moment in time. If you were to freeze a video, a car that's flying by, you freeze it at an instant in time, you could say the speed and the direction together will be your velocity at that instant. So we have one version of velocity that is instantaneous velocity, which we actually mathematically define with calculus. Just remember right now, instantaneous velocity means the velocity at a moment or instant in time. At a moment or instant in time. Or we could have average velocity, which would be the velocity, would be the average velocity over a duration or period. That's the average velocity over some duration or period of time. So you could think it might take me an hour to get to New Orleans, and my average velocity might be 60 miles per hour. But at different points in time during that trip, I had different instantaneous velocities. When I started out pulling out of my driveway, I was going really slow. My instantaneous velocity out of the driveway might have been 2 miles per hour. I might have gotten up to 80 miles per hour during my trip and spent a long time at 80 miles per hour. But then I slowed down again near the end, so my instantaneous velocity later on in the trip was lower. But the average velocity for the entire trip, well, that could just be 60 miles per hour. That's on average because you're talking about a whole duration or period of time rather than an instant. So let's say we need a definition here for our average velocity. Symbolize that with a V. A lot of times you'll see it with a bar over it because the bar actually means average. But we usually get tired of writing that, and you just use the context of the problem or the equation to determine if we're talking about average velocity or instantaneous. But the bar means average if you ever see that on something. Instantaneous velocity, you would just have the V. And notice my V's will always have this kind of little swoosh hook thingy on the left side so that it doesn't look like a U. That's generally how people write it in physics and stuff. So the bar means average, but average velocity is just going to be the total displacement divided by time. So we'll say average velocity, V bar, which remember, usually we're not going to be writing the bar, is going to be the displacement, not the distance, but the displacement, the total change in position divided by time. So if we're in the x direction, that means average velocity could be delta x over t, or delta t if you want to write that, the total change in position divided by the total change in time that corresponds with those positions. So if we wrote that out more, we could say that would be x final minus x initial. We know that's what the delta x is going to represent. And t you could just leave as t, or you could write it as the final time that corresponds with the final x position minus the initial time that corresponds with the initial x position. Our instantaneous velocity is actually a derivative when we write it mathematically, so we're just not going to do that because we're just dealing with the algebra here. So I'm also going to put a final note with the bar. We won't be writing the bar above the v. We won't be writing the bar. Over the v. Make sure that word actually looks like bar. You can if you want, but generally we get kind of tired of doing that. Okay, so there's our velocity. It's a displacement over time. That's the most important thing to remember. You can have instantaneous at a moment or instant in time, or an average velocity, which is something that you calculate over a duration or longer period of time. What kind of quantity is this going to be? Oh, velocity. Something special about velocity is that it is a vector quantity. It has both magnitude and direction, right? That's what our vector means. Magnitude is symbolized by a number and our units. So velocity is essentially going to be telling us how fast. It's displacement divided by time. So it's your change in position divided by how long that took for that to happen. So this is going to be telling us how fast and in what direction. Right now in linear kinematics, our direction is going to be symbolized with a plus or a minus. So if our velocity is positive, that means we are traveling in the positive direction, and it tells us our rate, how quickly. If our velocity is negative, it tells us we're traveling in the negative direction, and the magnitude also tells us how quickly. The direction can be positive or negative. Later it can be an angle. You could say to the north, to the south, something like that. So let's come over here and say velocity is how fast and what direction. How fast and what direction? Move my bar information over here. How fast and in what direction? That's our velocity. We can have instantaneous or average. It's a vector quantity. It's defined as displacement or delta x over time. Our last kinematic quantity is acceleration. You got to be careful in defining and thinking about acceleration, because a lot of times people think to accelerate means to speed up, but not for us. It does mean that sometimes. Acceleration means to speed up, slow down, or change direction. Acceleration tells us how we're speeding up, slowing down, or just changing direction, or a couple of those things at the same time. In linear kinematics, we're traveling in either the positive direction or the negative direction, so we're not dealing with turning. So we don't have to worry about the changing direction just yet. Like velocity, we have two types of acceleration we could talk about. Instantaneous. So that would be in an instant, at a certain moment in time. What is the acceleration? Or you could talk about average acceleration over a period of time, just like we said with instantaneous and average velocity. Now, with our class, what we do in this physics class is we only deal with constant accelerations, which means acceleration is either going to be one value, and it's constant, or it's zero, which still is a constant value, it's zero. So we don't have to really deal with changing accelerations at all, which is nice. The reason we don't is because you need calculus in order to do that. The symbol for acceleration is a. So average acceleration would have that bar over it, just like we mentioned with average velocity, but I'm not going to write it. We don't need it. Acceleration is the change in velocity, so I can write delta v divided by time, or change in time. So it tells us how quickly our velocity is changing. Acceleration is how quickly our velocity is changing. So if our velocity is, say, changing such that we are moving faster in the same direction, then our acceleration would be indicating the rate at which our velocity is increasing. How much are we speeding up? If our velocity were changing such that we were slowing down, our acceleration would tell us how quickly are we slowing down. And it also tells us our direction there too. So this is also a vector quantity. we spread out that delta v, we know it's going to be v final minus v initial over time. Look very similar to up there for velocity. It was delta x over t. Now we just have the next quantity, delta v over t. How quickly is velocity changing? This is, again, as I just mentioned, a vector quantity, meaning it has both magnitude, a number with units. So it's got a number with units, and then we also have a direction, which in linear kinematics is just going to be positive or negative, but eventually it could be something like an angle or to the north or something like that. Let's go back real quick, and we're going to say what the base units are for all of these things. Position just depends about what unit is on my thing up there, my number line, whatever I'm using. So if this is 0 to begin with, and then here 1 is 1 meter away, and this is 2 or 2 meters away, then I have my units built in already on my number line or my frame of reference. So that's how you can regard position. Displacement, by default we're using the base unit for length because displacement is a change in position through space. So the base unit is going to be the meter, which is the base unit for all length measurements. Base unit in SI system is meter. So in parentheses I put lowercase m, that's the symbol for that unit. Distance, same thing. Base unit for distance is going to be the meter. Same unit, but remember displacement and distance represent different types of quantities. One is a scalar, one is a vector. Time, our base unit is the second. So you can always use other units, right? You could use kilometers, you could use hours, but the base unit means the default thing. And that's based on the SI, the System International for units. Speed is going to be just like velocity. We're going to have, look, distance over time, except velocity is displacement over time. So if the units for distance are the meter, and the units for time are the second, then my base unit for this is going to be my meters per second, or meters divided by seconds, which we symbolize as little m divided by little s. Velocity, same thing, it just is a vector, so our base unit for velocity is going to be meters divided by seconds. Try to think, what's acceleration going to be? It's not going to be meters over seconds. Base unit for acceleration. Let's go back and think, what does acceleration mean again? Well, let's go even further back. Velocity was how quickly your position is changing. Velocity is how quickly your position is changing. Acceleration is how quickly your velocity is changing. So that's going to be your velocity, your change in velocity per unit time. You got to divide by another unit of time. You got to divide by another second. So the base unit for acceleration is going to be meters per second. Per second! That's a weird way to write it, though. No one's going to write it like that. But that's what it is. It's meters per second per second. So the way I would symbolize that with my symbols would be meters divided by seconds divided by seconds. But also no one's going to write it like that either. This is the same thing. It's equivalent to, 3 lines means equivalent to, meters divided by seconds squared. So acceleration is always going to be in a length unit, like meter, divided by squared time units. And the base units are going to be meters divided by seconds squared, or meters per second every second. How quickly is your velocity changing? A certain amount of meters per second every second. All right, that's it for the variables that we're using in linear kinematics. Go check out some of the stuff on motion graphs and practice some interactives. See you next time.